Hello and welcome to this lecture on advanced electric drives. In the last lecture, we have just started the speed sensorless vector control of an induction motor. The basic motivation behind the speed sensorless control is that in many industrial applications, speed sensor is not a very essential requirement. So, for example, in underground mining, when you use a drive in underground mining, the speed sensor, with the speed sensor, the drive becomes less robust. So, to make the industrial drive more robust, the ideal situation is to go for a drive without a speed sensor. So, the speed sensorless control has become a de facto industrial standard. We can go for a drive without any speed sensor. So, if you do not have a speed sensor, how can we go for closed loop speed control? There may not be any speed sensor, but the speed can be estimated from the terminal variables. So, today we will discuss about the speed sensorless vector control of induction motor. Now, when we do not have a speed sensor, we have to estimate the speed from voltages and current. These voltages and currents are the terminal variables. So, what we have to do is to estimate the speed from the terminal variables. So, estimation of speed from terminal variables such as voltages and currents. So, we will first derive the equations for the speed sensorless control, and then by means of a block diagram we will try to see how this can be implemented. So, we will write down the equation in the stationary reference frame for an induction machine. So, we are taking a stationary reference frame equations. So, we will first talk about the stator. The stator equations are VDS equal to RS IDS plus P psi ds in the d axis. Similarly, in the q axis we can have VQS equal to RS IQS plus P psi q. And we can also write down the expression for psi ds. Psi ds equal to LS IDS plus LM IDR. Now, as we have already seen that IDR is difficult to measure. So, we do not have any idea about the rotor current. So, we have to estimate this current, or we have to express this current in terms of the stator current and some other variables. So, we can replace IDR, and IDR is replaced in the following fashion: psi IDR minus LM IDS by LR. So, we have been able to replace the rotor d axis current by the following expression. Then if we simplify this, what we get is the following: LS minus LM square by LR into IDS plus LM by LR into psi ds. This can further be simplified as follows: psi ds is equal to LS into 1 minus LM square by LS LR into IDS plus Lm by Lr into psi dr. These are all in the stationary reference frame. So, the variables are in the stationary reference frame. Now, this quantity is called the leakage factor or sigma, because this is a measure of the leakage inductance of the machine. So, if sigma equal to 0, the leakage inductance of the machine will also be equal to 0. So, we can further write down this as sigma into Ls into IDS plus Lm by Lr into psi dr. Similarly, in the q axis, we can write down the equation for psi qs. It will be similar to what we have written, sigma Ls into IQs plus Lm by Lr into psi qr. Now, this we can substitute back in the voltage equation that we have already seen, that these are the two voltage equations. So, we can substitute for psi ds and psi qs respectively and simplify. So, if we substitute this back in the voltage equation, we get the following: Vds is equal to Rs IDS plus sigma Ls P IDS plus Lm by Lr into P psi dr. This is in the d axis, and similarly in the q axis we can have the equation Vqs, that is equal to Rs IQs plus sigma Ls P IQs plus Lm by Lr into P psi dr. So, the importance of these two equations are the following: if we know voltage and if we know current, we can estimate the rotor flux. So, this equation, these two equations shows that we can estimate psi dr and psi qr, we can estimate psi dr and psi qr from these two equations. So, we have psi dr here in the first equation and psi qr here in the second equation. So, we can estimate psi dr and psi qr from Vds and Vqs respectively. Now, let us write down the equation for the rotor. In a similar fashion, we can write down the rotor equations. So, in the rotor, we can start with the d axis equation. The rotors are short circuited. So, we can start with Vdr equal to 0. So, Vdr is equal to 0, that is equal to Rr IDR plus P psi dr, and then we are talking about a stationary reference frame, and stationary reference frame means the speed of the reference frame is equal to 0. So, we have a rotationally induced EMF, but that will be appearing as omega r into psi qr. So, we have in this case plus omega r into psi qr, because the reference frame has a velocity that is equal to 0. We are talking about a stationary reference frame. From this equation, we can, as we already done, this IDR is difficult to measure. So, we can replace for IDR. So, we can say 0 equal to RR. IDR can be written in terms of psi dr and IDS. Psi dr minus Lm IDS by Lr plus P psi dr plus omega r psi qr. This can further be simplified. We know that Lr by Rr is tau r. So, 0 equal to psi dr minus Lm IDS by tau r is the rotor time constant. Tau r is the rotor time constant, that is divided here plus P psi dr plus omega r psi qr, or we can say that P psi dr is equal to minus of 1 by tau r psi dr plus Lm by tau r into IDS minus omega r psi q r. So, this is the equation in the d axis. Similarly, we can write down the equation in the q axis. So, in the q axis we can have a similar equation. In the q axis rotor we can have a similar equation, and the equation will be p psi q r equal to minus 1 by tau r into psi q r plus Lm by tau r IQS plus omega r psi dr. So, these equations will help us to estimate the rotor speed, that is omega r. Now, this equation will also give us an estimate of the rotor fluxes. So, the rotor fluxes are psi dr and psi q r in the two axes respectively. So, if you want to find out the rotor flux angle theta e. Now, what is this rotor flux angle? The rotor flux is psi r, and we have stationary d axis and we have stationary q axis. This is our d axis and this is the q axis, and the rotor flux is rotating at a speed of omega e. It is rotating in the space with the synchronous speed, and the synchronous speed of the rotor flux vector is omega e. And this angle which is obtained with the stationary d axis is theta e. Now, if you want to find out theta e can be found out as follows. If we take the flux component, the component here is psi dr in the d axis and psi q r in the q axis. Now, if we project the rotor flux along the d and q axis respectively, we obtain psi dr and psi q r respectively. So, we have, this is our d axis flux, this is the q axis flux, and we are talking about the angle of the rotor flux vector, that is theta e, and that is given as tan inverse of psi q r by psi dr. So, this is what we have obtained here, and in this case if we find out what is omega e is the speed of the rotor flux vector, that is the derivative of this angle. So, omega e is equal to p theta e, and if you differentiate theta e with respect to t, we get omega e. Now, this is a differentiation in parts. So, we have tan inverse of psi q r by psi dr. So, we can differentiate in parts. So, we have 1 by 1 plus psi q r by psi dr square. So, we are basically differentiating tan inverse of psi q r by psi dr, and this has to be done differentiation in parts. So, we have 1 by 1 upon psi q r by psi dr square into psi dr p psi q r minus psi q r p psi dr by psi dr square. So, we are trying to evaluate p theta e, that is d theta e by dt, and this is given by the following expression. And if we simplify this expression, what we obtain is psi dr p psi q r minus psi q r p psi dr divided by psi dr square plus psi q r square. So, this is the expression for the synchronous speed, that is omega e. Now, we are interested to find out theta e, and we have to find out, ultimately we have to find out omega r. Omega r is the rotor speed. So, what we can do here, we take this equation and we replace for p psi q r and p psi dr from this expression. We know that we have the expression for p psi q r. Similarly, we have the expression for p psi dr. So, from these two equations we can obtain these values and substitute in the third equation. So, we can in fact name this equation, this equation is equation number 1, and this is equation number 2, and this we can call this equation number 3. So, we can substitute for P dr and P qr from equation 1 and 2 respectively in equation 3 and then simplify. So, if we do that, we get the following expression. We are evaluating omega e, that is P theta e, that is equal to psi dr minus of 1 by tau r psi qr plus Lm by tau r into iqs plus omega r into psi dr minus psi qr 1 by tau r into psi dr plus Lm by tau r into ids minus omega r psi qr. That is divided by psi dr square plus psi qr square. This is what we obtain. Okay. Now, if we simplify this equation, although it is a little complex, there is some scope for simplification. So, if we simplify this equation, we get the following. We will get omega r plus Lm by tau r into psi dr iqs minus psi qr ids divided by psi dr square plus psi qr square. And we can further simplify this. We have to obtain what is omega r. Omega r is equal to P theta e minus Lm by tau r into psi dr iqs minus psi qr ids by psi dr square plus psi qr square. So, we have to substitute the expression for P theta e. So, P theta e value is already known here. So, we see that P theta e is given by equation number 3. So, we can substitute the value of P theta e from this equation in the final equation here to find out the expression for omega r. So, if we do that, what we obtain here is the following. We get psi r psi dr P psi qr minus psi qr P psi dr minus Lm by tau r into psi dr iqs minus psi qr ids divided by psi dr square plus psi qr square. So, we have been able to obtain the estimate of omega r. Omega r can be evaluated by the following expression, that is expression number 4, equation number 4. So, the equation number 4 will give us an estimate of omega r, and in this equation we know that psi dr can be evaluated, P psi dr can also be evaluated, and ids and iqs can be measured. So, we in fact know all the variables in this expression in the right hand side of the equation, and when we know everything on the right hand side, we can evaluate it what is omega r. This omega r is the rotor speed, can be evaluated from the equation, that is equation number 4. Now, this can be explained by means of a block diagram. So, we can show this in the form of a block diagram. Block diagram for speed estimation. So, here we start with the estimate of the fluxes. So, what we have here, we can use the information of the current and the voltages. This is Rs plus sigma LSP, this goes here, and the input of this this is VDS, this is IDS, and here we have minus and plus in this case. Then we have LR by LM, and what you obtain here is P side here. So, the rotor flux in the D axis can be estimated from the voltage and current, that is VDS and IDS. Similarly, in the Q axis we can have VQS and we can also have IQS, and this is negative and positive here, and we multiply in this case LR by LM, and what we obtain here is P psi QR. And then we use an integrator, we integrate this to obtain psi dr, we integrate this quantity to obtain psi QR respectively. And we use a multiplier also here. We can also use a multiplier in this case. This multiplier, one of the input is P psi dr and the other input is P psi QR. And here in this multiplier we take the signal from this side, then we subtract. So, after subtraction we get one part psi dr P psi QR minus psi QR P psi dr. So, this part can be obtained after subtraction. In a similar fashion, we will use another multiplier here, and we will multiply in this case IQS. Similarly, here we can also have a multiplier. We can multiply here IDS, and we can take this signal, we can find out the square of the signal. We have a multiplier and then we can multiply the same thing, and what we obtain here is psi dr square. Similarly, we take this signal, we use a multiplier and then we multiply the same thing here, we obtain psi QR square. And we can use a summer in this case, we can add psi dr square and psi QR square. These two are positive in this case, and this can be used in a divider. As a denominator, and the numerator can be obtained in the following fashion. This is what we have is a positive in this case, and then from this we can use another subtractor followed by a gain block Lm by tau r, and this goes to the subtractor, the negative sign here, and this gain block, other input to this subtractor comes from this multiplier. And finally, This is the numerator of the ratio. So, this block diagram shows how we can estimate the rotor speed. So, what we have here, we are basically taking this VDS and VQS from the machine terminals. We have VA, VB and VC. From that we can find out what is VDS and VQS. Similarly, we can have current sensor to sense IDS and IQS. So, from this we can evaluate the rotor fluxes, psi dr and psi qr, and the derivative of the corresponding fluxes, and then we can evaluate the ratio which will finally give us the rotor speed. So, this is our point of interest. What we want is the rotor speed, and the rotor speed can be obtained from the terminal variables. So, this estimator is called an open loop estimator, because this does not have any error correction mechanism. In fact, if there is some error in the measurement, there is no way we can correct the speed estimate, and hence we can call this to be an open loop estimator. So, this estimator is called an open loop estimator. Because there is no error correction mechanism. So, to have little more error correction mechanism, in fact, if there is some error in the measurement, there has to be some correction mechanism to correct the speed estimate. So, the open loop estimator does not have any error correction mechanism. So, we go for what is called a closed loop speed estimator. So, we will see how we can implement a closed loop speed estimator. So, here we rely on the principle of vector control. Of course, we have to understand that this is basically for vector control, and we know that we have these equations psi qre is equal to 0 and p psi dr e also equal to 0. So, this is for rotor flux orientation, and we know that psi dr e is equal to Lm into IDAC by 1 plus tau r p. This we have already evaluated when we talked about rotor flux oriented vector control. We saw that whenever we are varying the flux component of current, IDS is the flux component of current, the flux is delayed, and the delay is by rotor time constant. So, this is the flux component of current, and if we change this, the flux response will be delayed by the rotor time constant. So, these two equations will, and also we know that the expression for slip speed is equal to 1 by tau r into IQS by psi dre. So, this is the expression for the slip speed, which you have also evaluated for rotor flux oriented vector control. Then from this equation, the equation from the flux, we can simplify this tau r into p psi dr e, that is equal to Lm into IDAC minus psi dr. So, we can call this as maybe equation number 1, this as equation number 2, and this as equation number 3. So, these 3 equations will help us estimate the rotor flux in a closed loop fashion. So, we will see by means of block diagram how we can estimate the rotor flux in a closed loop fashion. So, we will see closed loop speed estimator. So, we will start with our original voltages and currents. So, this is my voltage VDS, and this is the current, that is IDS, and we have RS plus sigma LSP as we have seen earlier. We have a subtractor. Then what we have is 1 by P LR by LM, and this is giving us psi dr. And similarly, in the q axis, we can have the currents and the voltages Rs plus sigma LSP, this is IQS minus, and then we have VQS, we have 1 upon P LR by LM, and this will be giving us psi QR. So, this flux psi dr and psi QR are estimated even in the previous expression. So, this we have also evaluated here from the voltages and currents, and from psi dr and psi QR we will try to do some way, some technique to estimate the synchronous speed. Now, we know that whenever we have a rotor flux which is rotating at a speed of omega e, we have two different components. We have d axis here and we have q axis here, and this angle is theta e, and if we project this psi r on the d and q axis respectively, we can take the projection of this is called psi dr, and if we project this on the q axis, we call this to be psi qr. So, psi dr and psi qr are the projection of the rotor flux vector on the d and q axis respectively. So, we can in fact evaluate what is psi dr and psi qr in terms of psi r. So, we will say that psi dr is nothing but psi r into cos of theta e, this we can say here, and similarly we can say that psi qr is equal to psi r into sine of theta e, because the d axis is the cos component and the q axis is the sine component. So, we have evaluated here psi dr and psi qr from the voltages and currents, and then what we do here, we multiply. What we multiply in this case with the psi dr, we multiply sin theta e. So, we multiply with psi dr sin theta e, and we multiply with psi qr cos theta e. So, if we multiply sin theta e with psi dr, it means what we are trying to do here, we are multiplying sin theta e here with psi dr, and sin theta e will also available in the right hand side. I have sin theta e here, and with psi qr we are multiplying cos theta e. So, I can have this in the left hand side, also in the right hand side. So, we can see in this case that sin theta e into psi dr is equal to psi r into cos theta e into sin theta e, cos theta e into psi qr is equal to sin theta e into cos theta e. So, in fact, these two quantities are the same. So, what we can do here, we can have in this case subtractor, and the subtractor is going to give us 0 value if the estimate is correct. So, I am subtracting this from that, and then we are using a simple PI controller which is Kp plus Ki by S, and then this is integrated. This is giving me the synchronous speed, this is integrated, and what I obtain out of this is theta e, and the theta e is used as a feedback for cos theta and the sin theta respectively. So, here we have an error correction mechanism. If the estimate is correct, we will have a 0 value here, this will be 0, and if the estimate is not correct, this PI controller will be giving me a finite output, and I will automatically have a correction mechanism inbuilt here. So, we were discussing about the closed loop speed estimator for an induction motor, and we have an error here. The error is in this case E, which is the subtraction of psi QR cos theta E and psi dr sin theta E, and both are the same. We have already seen that these two quantities are exactly same. So, in the steady state you can see that if the estimate is correct, if the value of theta E is correct, this is going to give me that is equal to 0. And we have PI controller following the error, and this will have proportional gain and an integral gain Kp and Ki by S. The integrator will be sufficient to give me a steady state value. Even if the input equal to 0, the output will not be equal to 0, because we have an integrator in this case. So, this output is omega E here, and we can integrate this omega E to obtain theta E, and the theta E is fed back as sin theta E and cos theta E for this comparator. So, from this what we obtain theta E, and we obtain omega E. So, this estimator is going to give us omega E and theta E, and we have to use some other technique to evaluate the speed. It means if you can have slip speed, you can find out the rotor speed by subtracting the slip speed from the synchronous speed theta E. So, we have the transformation block here that we have already used, and in this case we can measure IDS and IQS. They are the stationary reference currents, IDS and IQS. We can use the transformation, and the transformation can have theta E as obtained from the previous block diagram. So, this theta E that we have obtained here can be fed back to this our theta E, and this transform can transform this IDS and IQS into IDS E in the rotor flux reference frame IDS E, and similarly IQS E. This IDS E and IQS E are the variables in the rotor flux reference frame, and from IDS E and IQS E we can do some operation to find out the slip speed. So, what we do here is that we multiply in this case Lm, the magnetizing inductance, and then we use a subtractor, and here is 1 by tau r. We integrate this, and this output is tau r into psi dr E. So, as per this equation we can see that we can use this equation that tau r into p psi dr equal to Lm IDS minus psi dr. So, if we take the right hand side, we will subtract Lm IDS minus psi dr E, and that will be giving us tau r into p psi dr, and that we see in this block diagram, and finally the result is tau r into psi dr, and that we are using in a divider. In the divider we can use this as a denominator, and this is the numerator, and this is going to give us the slip speed omega SL, because we know that omega SL is given by 1 by tau r into IQSE by psi dr. So, we have psi dr into tau r, and we also have IQSE by the transformation. We have obtained IQSE, and from this two we can find out what is the slip speed, that is omega SL. And we know that we have already evaluated omega E. So, what we can do here, we can again use a subtractor. This is minus, and we can use the signal omega E that is already available here in the previous block diagram. So, this is already known. So, this omega E can be fed here, and what we finally obtain out of this is omega r. So, this is our estimated rotor speed. So, this actually is a method of estimating the rotor speed in a closed loop fashion. This is called closed loop because we have an error correction mechanism, and the error correction mechanism is available here. We are using a PI controller following an error. In the steady state, the error is going to be equal to 0. Unless the error is 0, the PI controller will be giving an action to either increase or decrease the value. So, omega e will be so adjusted that the error becomes equal to 0. So, the speed of the flux vector is omega e, that is going to be adjusted by this mechanism, and hence this is called a closed loop speed estimator. And this estimator will definitely have better performance than an open loop one, in the sense that whenever we have an integrator, there is a scope of error. But in this case, since we have a PI controller, this error will be minimized, and omega e, the speed of the rotor flux vector, will be very accurate. And if omega e is accurate, theta e will also be accurate, and from that we can evaluate what is the slip speed, and from the slip speed and omega e we can evaluate the rotor speed. So, this is practically implemented in many applications where we do not need any speed sensor. So, with this background, we have already discussed about the rotor flux oriented vector control, the air gap flux oriented vector control, and the stator flux oriented vector control, and we now understand what is the meaning of vector control of induction motor. Now, we will show by means of a problem how we can tackle problems in vector control, and especially we have already seen that the air gap flux oriented control and the stator flux oriented control are little complex, and they are not very much in use. The most popular vector control method is rotor flux oriented vector control. So, today we will solve a problem on rotor flux oriented vector control. So, let me write down the problem statement. This is a numericals, and we have to solve this particular problem. The problem is as follows: a 400 volt 50 hertz 4 pole 1370 rpm star connected induction motor is supplied from a current regulated PWM voltage source inverter. And is operated with rotor flux oriented vector control. The motor parameters are given as follows: the parameters are Rs equal to 2 ohms, Rr prime referred from the primary side is 5 ohms, the leakage reactance of the stator same as the leakage reactance of the rotor referred from the primary side, that is 5 ohms, and the magnetizing inductance is equal to 80 ohms. all reactances are calculated at 50 Hz. Neglect core and friction losses. Now, what we have to find is the following. We have to find the required values of IDSE and IQSE to operate the motor at rated speed if the terminal voltage and frequency are held at rated values. Calculate the torque and slip frequency, that is in radian per second, under the condition in A. So, this is a problem which you have to solve, and this is on rotor flux oriented vector control. So, we have to first understand that this says that the machine is operated under rotor flux oriented vector control. The machine parameters are the voltage, the frequency is given, number of pole is given, the rated speed is given, the configuration is star connected, and it is fed from a PWM inverter under current control. The parameters are also mentioned here. These are basically the equivalent circuit parameters of an induction machine. They are very well known, so they are given here. So, we have to find out IDS and IQS. To operate the motor at rated speed, the speed is the rated speed, that is 1370 RPM, and the terminal voltage is the rated terminal voltage. The frequency is also the rated frequency. The terminal voltage and the frequency are held at the rated values. And we also have to calculate the torque and the slip speed or the slip frequency as in the condition A, as shown in A. So, we will make some attempt how to solve this problem. In this problem, what we have to do is that we have to first draw the equivalent circuit of an induction machine. So, the equivalent circuit looks like this. So, we have the steady state equivalent circuit of an induction machine per phase. This is the applied voltage per phase is 400 by root 3 volt, and this is the stator resistance, the stator leakage reactance, the rotor leakage reactance, and the rotor resistance and the magnetizing reactance, and the values are already given: 2 ohms, 5 ohms, this is 5 ohms, this is 80 ohms, and RR is 5 ohms. So, we have 5 by the slip S. So, this actually the equivalent circuit, and in this case we can find out the rated slip. So, the rated slip is given as 1500 minus 1370 by 1500, that is equal to 0.0866. So, we have all these parameters of the machine available to us. We have the voltage, we have the frequency information is also given to us. So, we can find out the impedance of the machine seen from this side, and we can divide and find out the stator current Is. So, in the next lecture we will be discussing this in detail, how to find out the stator current, how to find out the corresponding torque and flux component of current, and the slip speed of the induction machine.